तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This will be lecture number 22 on the series on mechanical measurements. Towards the end of the last lecture, we were looking at how a strain gauge is used for measurement of displacement or strain, and in fact we were looking at the elementary circuitry, which is the Wheatstone bridge, which is used for determining the changes in the resistance in terms of an imbalance voltage. So, what I plan to do today is to continue from there, just recapitulate what we did in the last class, and then look at one or two simple examples to find out what we expect from strain gauge circuitry, and then we will move on to the example of a diaphragm gauge, for which some of the basic formulae were formulated or given in the last lecture. So, we will take an example to look at what to expect from a diaphragm gauge in terms of the thickness of the gauge, the diameter, and so on and so forth. Subsequently, we will look at another way of measuring displacement, which of course can be used for measuring displacement in its own right, or for measuring displacement consequent to a pressure signal which is converted to a displacement signal by using either a diaphragm gauge or a Bellows gauge. The use of the LVDT, or the linear variable differential transformer as it is known, requires the understanding of the circuitry, how it is going to function, and also some principles of operation of the circuit and how it is used. This will form the latter part of the lecture. So, in essence, the present lecture looks at the measurement of displacement and relates it to pressure, and by two different methods, one using the strain gauge, the second one using an LVDT as the transducer, which changes the pressure signal through a diaphragm or a bellows to a change in displacement or a movement, and then that is sensed by using the LVDT, which is essentially an electrical means of looking at the displacement. So, let us look at the method of measuring the strain. So, we will go back to the strain gauge circuitry, which we talked about in the last lecture. Basically, a bridge circuit, in fact we called it the quarter bridge. We were just about introducing this terminology. So, essentially the quarter bridge circuit consists of the following. We have 4 resistances arranged in the form of a bridge, which is very familiar to all of you. So, we numbered them as R1, R2, R3 and R4, and we have a input voltage impressed by using a battery. So, this voltage is V supply, and we are going to measure the potential difference across these 2 points, and this we call that V0 or VO. And if you remember, towards the end of the last lecture, we said that this will be the strain gauge element, and the resistance of this particular element is going to vary because of the displacement or because of the straining of the element. We also mentioned something about the values of these resistors. Normally, the resistance of a strain gauge in the unstrained condition, that means that without any strain being impressed, unstrained resistance, or we can call it the base value, is either 120 ohms standard or 350 ohms, and we were actually talking about one of them, the 120 ohm case. The balance requires, balance means, in bracket I will write it V0 equal to 0 for any value of Vs, whatever be the value of Vs, the value of the output voltage will be exactly equal to 0 if the bridge is under balance, which requires, in this case what we are going to do is, we are going to look at the balance under the unstrained resistance case, in which case we will say that R1 is equal to R2 is equal to, I will say, R3 I standing for the unstrained case. You can call it the initial value before a strain is introduced, equal to R4. Actually, you know that we already know that the ratio R1 to R4 equal to R2 R3 divided R1 by R4 equal to R2 by R3 is actually the condition for balance. And if all the resistors are equal, the balance is of course going to be satisfied. We also saw in the last lecture that when the resistance of the strain gauge changes here, what will happen is that the voltage across this VO, which is the output voltage, is going to become either positive or negative depending on the direction in which the resistance is going to change. Okay. If it is compressive or if it is compressive strain or elongation. If it is elongation, what happens? The resistance R3 is going to change to a higher value, R3 will increase. This is what we have seen from the basic theoretical framework of the strain gauge, R equal to rho L by A, and we have discussed already the way the length is going to change, the elongation, and the area is going to change because of the Poisson ratio. So, we already know this, and therefore, if it is under balance with all the resistance being equal, when the resistance R3, which is the strain gauge, is in the unstrained condition, we have the balance. And now, we would like to know what happens when the resistance or the strain gauge undergoes a change in length, which means there is a strain imposed on that. Okay, this is what we are going to look at. Let us look at the relationship between V0 and Vs, which I gave in the last lecture. We will recapitulate that. We will write down the value. We saw that V0 by Vs, the ratio of the output voltage, the input voltage, V0 by Vs is given by R3 R1 minus R2 R4 in the numerator divided by R2 plus R3 into R1 plus R4. This is the expression. In fact, you see that if the numerator vanishes, there is balance. That happens if R1, R2, R3, R4 are all equal, it is going to vanish. This is what we saw in the last slide, the previous expression. Suppose the strain gauge undergoes a small change in the resistance because of strain which it experiences. So, R 3 is equal to R 3 I originally. So, I will just modify it here R 3 I. It changes by a small amount to R 3 I plus d R 3. A small change is going to take place, okay, because of the strain. So, all I have to do is to wherever R 3 I is there, I replace it by R 3 I plus d R 3, and then we will make the approximation that d R 3 is very small compared to, or the change in resistance small compared to R 3 I, and therefore, in the denominator of this expression I should replace it by R 3 I plus d R 3, but I will ignore the R 3 in that. And also in the previous page we have indicated that R 1 equal to R 2 equal to R 3 I equal to R 4. So, we will impose that condition in this case. So, if I do that, this will be R 3 I R 1 minus R 2 R 4. So, what I am going to do is I am going to change R 3 I to R 3 I plus d R 3. So, what I will do is I will write the expression here V naught by V s equal to R 3 I plus d R 3 multiplied by R 1 minus R 2 R 4 divided by, I will approximately say that is equal to R 2 plus R 3 I multiplied by R 1 plus R 4. Actually, we had done this exercise earlier, I am just recapitulating, and you remember that R 3 I minus R 1 minus R 2 R 4 must be cancelling each other, because that is the condition for balance when there is no strain in the strain gauge element. Therefore, this portion is going to cancel off with this. So, you have R 1 d R 3, and now I will assume that all these R's are the same, because R 1 is equal to R 2 equal to R 3 I is equal to R 4. So, this becomes, so let us assume that they are all equal to some value R. So, I will say this is R into d R 3 divided by, this will be R plus R 2 R, this will be another 2 R, this becomes 4 R squared, and its R will cancel off with this. So, you see that the ratio V 0 by V s will become d R 3 by 4 R. So, the change in resistance divided by the original resistance divided by factor of 4 is the value of V 0 by V s, and we already know d R 3 by R is related to the strain by the relation which we gave in the last lecture. So, what we can do is we can write this d R 3 by R as epsilon into 1 plus 2 nu. So, if you remember, d R 3 by R was related to the strain, and it was related through the expression epsilon into 1 plus 2 nu. So, we can rewrite this in terms of the strain, which of course, it can be done any time one would like to do that. So, let us look at this expression and look at a simple example. So, what I will do is I will say d R 3 by R, R is nothing but R 3 I. I am writing it as R because we have made that clear earlier. This will be some S times epsilon in the axial direction, where epsilon A is the strain of the element, okay, So, introducing this into the previous expression and rearranging, I am going to get the following: the strain epsilon A is equal to 4 times V 0 by V s into 1 over S. This is the expression which is going to relate the strain to the output voltage. So, in order to appreciate the types of numbers which are involved, let us take a simple example, so that we get an idea of the kinds of numbers we are going to have. So, I will take the example which I will call it example 22. I think we are just keeping track of the number of examples we have used in this set of lectures. Suppose I have a gauge factor, S is nothing but your gauge factor, which was roughly equal to 2. We will just make the assumption here is equal to 2, and we will assume that the input voltage V s is 5 volts, and all the resistors are equal, all the resistances are equal in the unstrained state for the strain gauge, and each one equal to R equal to 120 ohms. So, we would like to see what is the kind of strain we are going to get if the output voltage is measured. Suppose V 0 has been measured to be equal to 1.13 millivolts. How do we measure this kind of a small voltage and so on, we will come to a little later on. So, this is given. So, I would like to know what this corresponds to in terms of the strain gauge. That is what the problem is. So, we will just have to use that formula which I wrote in the previous page. So, the formula you can recapitulate: epsilon A equal to 4 V naught by V s into 1 over S. It is a very simple formula. So, this will be 4 into 1.13 millivolts, that will be multiplied by 10 to the power of minus 3 volts, divided by 5 volts 1 over 2 of that, and this comes to 0.000452, or if you write it in terms of micro strains, it will come to 452 micro strains, which is written as mu strain. So, the strain of the strain gauge element, which gives an output of 1.13 millivolts, when the 4 resistances are of equal value in the balance condition, and all the resistance, each resistance equal to 120 ohms in the balance condition, gives me for 1.13 millivolts I get a strain of 452 microstrains. So, we are talking about very small changes in the length. 452 microstrains is nothing but 452 into 10 to the power of minus 6, which is equal to delta L by L. So, you can find out if L is given, delta L will be 452 into 10 to the power of minus 6 of that length L. So, it is a very small strain which we are talking about, and the assumption that the strain gauge is within the elastic limit is very well satisfied with such small strains, and therefore, whatever we have done seems to be okay. Now, suppose I look at the same problem slightly differently. I will call it the example 23. I would like to look at the change in the resistance in this particular case. So, the strain is given as the number Actually, what I will do is I will slightly change the problem a little bit. So, the strain is given as 1000 microstrains. So, it is easy to work out the numbers. So, I want to find out if the strain is actually equal to 10 to the power of 3 microstrains, what is the change in the resistance? Change in the resistance is needed to be obtained. What is the change in the resistance? So, if you remember, we have delta R by R from the strain gauge theory is nothing but 2 times delta L by L. This is the 2 is the gauge factor, and therefore, I can say that delta R equal to 2 into R delta L by L, 2 into 120 ohms, delta L is 10 to the power of 3, delta L by L is 10 to the power of 3 microstrain, which will be 10 to the power of 3 into 10 to the power of minus 6, and if you work it out, it comes to 0.24 ohms. So, the change in resistance is very close to being about quarter of an ohm. The 120 ohms is the value of the resistance, and because of 1000 microstrains which has been imposed as a strain on the element, the resistance has changed by a value of equal to 0.24 ohms. So, the question is, how can we measure such small changes in resistance? So, we are going back, as it were, to describe why we are using a Wheatstone bridge. A Wheatstone bridge is initially balanced. That means, all the resistances are equal, and this small change in resistance is going to create an imbalance. This imbalance is going to be available as a small change in the voltage, and the small change in voltage can be easily measured by using, if necessary, an amplifier, and then the output can be monitored. So, the idea is to create, if I take a suitable supply voltage, I can get a sizable value for V 0. Microvolt or millivolts is easy to measure, either by using directly using a millivolt meter, or I can use an amplifier and use a regular voltmeter to measure the voltage. So, this is what one can probably do. Let us look at that part of the problem. So, the resistance has changed by a very small value, and because of this, the voltage which is appearing across the terminals, if you go back to, I think it was we are talking about this V 0, V s is the input voltage, and I think we had, this is the expression I am talking about. Output volts is given. In fact, output volt is not given, but I have been given epsilon A. I can work backwards and find out what is the output voltage for this particular case. So, we will look at the output voltage is given by V s into S epsilon A divided by 4. This is for a quarter bridge circuit. So, we can substitute, this will be 5 volts, S is 2, epsilon A is 10 to the power of 3 micro strains. So, 10 to the power of 3 multiplied by 10 to the power of 6 with a negative sign divided by 4. This gives 2.5 millivolts as the output. So, this is either directly read by a millivolt meter, directly read if you have access to a millivolt meter, or we can use an amplifier of a suitable gain. For example, if I use a gain factor of 10 to the power of 3, 1000 gain, the output will be like 2.5 volts, which can be measured using an voltmeter. So, measure using with a voltmeter, and we are working with DC potentials. All the voltages are DC, direct current, therefore, there is no real problem with this measurement. Now, we will look at one or two important things which you have not looked at till now. If you remember, when we were talking about temperature measurement using resistance temperature detectors or RTDs, we talked about something called self heating. Self heating is because a current is passing through the resistance, and because of the Joule heating, there will be a certain amount of heat produced, and depending on the rapidity with which this heat can be lost from the detector will achieve some temperature. It will attain a temperature which is higher than what it should be. So, self heating is going to change the resistance of the detector because of the temperature change, and a strain gauge is nothing but a resistance. And if you look at the circuit we are using, we were talking about using a circuit like this, and of course, there will be a current passing through this, and the current will branch out into two portions. One current will go here and one other current will go through that, and therefore, each one of these resistance R1, R2, R4, R3 are going to carry a current. And if these currents are all the same, and if all of them have the same resistance coefficient for resistance for change in temperature, probably they will all cancel out, but it is not necessary that it will happen. So, temperature compensation will have to be done, and if you remember, in the previous lecture we talked about the dummy gauge, and the dummy gauge is going to be in the other arm. There are two R3 and R4. R4 is going to be dummy gauge. The dummy gauge is going to be in the vicinity of the gauge which is going to be actually used for measuring the strain, and if these two are going to have the same kind of characteristics, the dummy gauge is the same gauge, but it is not going to respond to changes in the strain. There is no strain induced in this one, therefore, it responds to any temperature change, whether it is due to self heating or that is self heating is one possibility, or changes in the temperature of the ambient. Both of these are going to affect the resistance. Therefore, if I put the important thing to remember is, if R4 is the dummy gauge and R3 is the actual gauge, okay, this is the gauge, strain gauge, and this is the dummy gauge. These two, whatever changes take place, they will cancel each other. That is a very important thing. You should put it in the arms like this, R3 and R4. If you put the dummy gauge here and the actual gauge here, these effects will more or less nullify. But there is another important effect, that is of the lead wire resistance. In fact, if you recall, when we were talking about the RTD, we talked about the 3-wire arrangement and the 4-wire arrangement. So, whatever we discussed there should be possibly of use here also, because the same principles are involved. We are talking about using a Wheatstone bridge, and we are talking about lead wires, and therefore, it is common to use a 3-wire system. 3-wire system. So, let us look at the 3-wire system and discuss how it performs. So, what I will do is I will draw a simple sketch here. This is the gauge, which I will call as R3. I will always use the symbol R3 for the gauge, and it has 2 leads, and these are the 3 lead wires which are going to come out of that. So, this is R L, this is also R L, this is also R L. These are the 3 lead wires coming out of the 2 ends of the strain gauge. Okay. Now, what I am going to do is, I am going to connect this to R 2, on the other side I am going to connect R 4, and here is R 1, and I am going to measure the output V over here, and I am going to impose the supply voltage here. This is the Vs. Okay. This is positive and negative terms of the battery, and I am going to monitor this. So, by the arrangement like this, what has happened is, if you look at this R L is added to R 2, this R L is added to R 2, because I am measuring the imbalance voltage between this point and this point. If you want, you can call it A B. Imbalance voltage is measured across A B. So, if you look at this arm, actually it is R 2 plus R L, and if you look at this arm, this is R 3 plus R L. Therefore, I am adding a common value of resistance to these 2 sides, and therefore, if I look at the balance equation, let us see what happens. R 3 must be replaced by R 3 prime equal to R 3 plus R L in the expression which we used earlier. I am going to use R 2, I am going to replace R 2 prime is equal to R 2 plus R L, and let us look at the expression which we had earlier. So, the expression for V 0 by V s, which I wrote down earlier, will have to be modified. This will be R 3 prime R 1 minus R 2 prime R 4 divided by R 2 prime plus R 3 prime into R 1 plus R 4. R 1 and R 4 do not change. The lead wires resistances are going to affect only R 2 and R 3. And now I will substitute the values. R 3 prime is R 3 plus R L multiplied by R 1 minus R 2 plus R L into R 4, and we have R 2 plus R 3 plus 2 R L multiplied by R 1 plus R 4. And remember, R 1 to R 4 are all the same. That is how we have built up the bridge. Okay. Therefore, this R 1 into R 3, R 4 into R 2, they will cancel each other, and R 1 into R L, this R 2 into R L will also cancel each other under normal circumstance. Okay. That means that the balance is not going to be affected by the presence of the lead wire resistances. So, you can say that under the unstrained condition, under no strain condition, balance is not affected by the lead wire resistances. This is a very important observation we are making. So, the lead wire resistances are going to compensate each other, and therefore, the balance condition under no strain is not disturbed. Now, let us see what happens when the balance is not there and the resistance R 3 has changed by a small amount. So, in fact, if you would like to look at it, I can make it R 3 I here, R 3 I here, to be consistent with our earlier notation. Now, what I am going to do is I am going to perturb this R 3 by a small amount, and remember that R 3 I is equal to R 1 equal to R 2. So, So, here also I can make that equal to R 4 equal to 120 ohms or whatever, equal to some R, let us say, whatever may be the value. So, I can in fact simplify this expression by putting all these resistance equal to R common value, and before we do that, let us just look at what happens in the unbalanced condition. So, in the unbalanced case, R 3 I becomes R 3 I plus d R 3. So, this is due to strain. Due to the straining of the strain gauge, there is a small change in the resistance, and therefore, I can substitute into that and write the expression for that. So, we can simplify. So, we will say unbalanced due to change in the resistance R 3 by a small amount. This will give you delta R 3 or d R 3 divided by 4 R into, I will get an extra, instead of 1, I will get 1 plus beta, where beta is equal to R L divided by R. You can see that how it comes out. You have R 2, in this case here R 2 plus R 3, this is here, plus 2 R L, and R 2 equal to R 3 I. So, this becomes 2 R. So, I am taking the factor 2 outside, R also I am taking. So, 2 you can see that R 2 plus R 3 I plus 2 R L is nothing but 2 R plus 2 R L is nothing but 2 R into 1 plus R L by R. So, this 2 R into 1 plus R L by R, I am calling it as 1 plus beta, and that is what I wrote down in the next page. So, you see that balance condition is not disturbed when the strain is not there in the strain gauge. That means that the lead wires are compensated, and the equation for the output voltage as a fraction of the input voltage is the same as the earlier d R 3 by 4 R, but with a small factor in the denominator, which is a constant factor. That means that because 1 plus beta is greater than 1, this is less than d R by 4 R, which we got earlier. Therefore, there is a slight reduction by a constant factor in the response. So, a constant factor is not a problem. If there is a constant factor, it is not a problem. If it varies only, we have to worry. That means that there is a degradation in the performance of the circuit, because the output is slightly smaller than earlier, but it is independent of the size of the change in the resistance, and therefore, independent of the size of the strain, and that is what is desirable. So, the lead wire compensation, by having a 3-wire arrangement for the gauge, does the following two things. One, it does not change the null condition in the under the balance condition when there is no strain in the strain gauge, and the secondly, it reduces by a constant factor the output when the strain gauge has undergone a change in its length. Okay. So, this is a very important thing to know, and let us just take a simple example, the same kind of example we had earlier. For example, in the earlier we had all R's equal to 120 ohms and suppose we assume that RL is equal to 10 ohms, just an example, it is a possible, it could be even larger. Okay. Suppose the lead wires, for some reason you require a long lead wire and the lead wire has got a large resistance equal to 10 ohms. Important thing to remember, these two lead wires are going to run very close to each other, maybe in the same sheath together, and both of them are going to respond to the same changes in temperature of the surroundings, if there is some change at all, and because they are in the two opposite adjacent arms of the bridge, these effects will cancel. That is very important to remember. The lead wires, they are made to go close to each other, they are taken in the same sheath. If they are subject to any temperature variation, they are going to undergo same changes in temperature, and if RL changes by a small amount, both the RLs will change, and therefore, it is not going to affect the measurement. That is very important too. So, the temperature's compensation is because they are in the two adjacent arms of the bridge. So, we can determine the value of beta will be nothing but RL by R, which will be 10 divided by 120, which will be 1 over 12. So, now I can determine V naught by V s for the same case we studied in the first case, that is 10 to the power of 3 microstrains. This is the epsilon A is given. So, for this case, and also the voltage V s is 5 volts. I am taking the same example. So, V naught by S is V s now is going to become S by 4 multiplied by epsilon A divided by 1 plus beta, and this will be S is 2 by 4 into epsilon A is 10 to the power of minus 3, because 10 to the power of 3 and 10 to the power of minus 6 divided by 1 plus 1 over 12, and it comes to 0.462 millivolts per volt. If I substitute V s equal to 5 volts, V 0 will be equal to 5 times 0.462 millivolts. And you compare with the previous value, when beta is 0, this will be nothing but 2 by 4 into 10 to the power of minus 3, this is 0.5 millivolt per volt if beta equal to 0, that is no effect of the lead wire resistance, or the lead wire resistance is very small, then you will have 0.5 millivolts per volt. So, the change in the output or change in the response in percentages will be nothing but, actually it is a decrease. So, we will indicate by an arrow going down, is 0.462 minus 0.5 divided by 0.5 into 100, and this is about minus 7.6%. So, a constant value of minus 7.6% is the reduction in the response of the strain gauge because of the lead wire resistances. In fact, in practice, the equipment or the experimental setup in which we are going to measure the, in this case of course the pressure, or in the general case it may be the strain of a member which is going to be loaded. It may be a big equipment in which we are trying to make the measurement of the strain. So, the wires have to necessarily go a long distance from the place where the strain gauge is mounted to the meter, which is going to be probably several meters away, meters in the sense that lengthwise quite far away, and therefore, you need lead wires. So, these lead wire resistance cannot be avoided, and if the length is large enough between the place where we are making the measurement and the electronic equipment which is sitting somewhere away from it, there will be the lead wire resistances may be in this case 10 ohms, it may be even more. So, the lead wire resistance cannot be avoided. because it is required because of the placement of the equipment in the laboratory space. In the case of process measurement, the process pressure which is being measured may be several tens of meters away from the control room. Control room is where we are going to monitor the pressure and temperature and other process parameters, and the pressure gauge itself may be located very far away from the control room, in which case again you are having a large length of wire running from the gauge to the electronic equipment. So, the RL could be large, 10 ohms or 20 ohms or even 50 ohms, but if the 3-wire arrangement is used, the effect of that will be eliminated, excepting that it is going to degrade the performance of the VO by Vs is going to be degraded by a constant factor. In this case, it is going to be 1 over 1 plus beta, where beta is the ratio of the resistance of the lead wire to the resistance of the gauge or the resistors which are used in the piston bridge circuit. So, with this background, we have basically covered the measurement of pressure using strain measurement using a strain gauge. And so, what I will do now is to take a look at alternate methods of displacement measurement. As I mentioned in the last lecture, displacement measurement is also an important activity in the under the mechanical measurement category, and instead of describing the measurement of length or displacement separately as a separate set of lectures, I have sort of introduced or dovetailed into the present discussion, because it is very convenient to do so. So, it is very clear that in its own right displacement may have to be measured. In fact, there are many other methods which will be probably covered in the metrology part of the course. So, what I am going to do is to look at the alternate method. One of the alternate methods is use of a linear variable differential transformer, which I referred to earlier in passing. So, the pressure signal is converted to a displacement in the case of a diaphragm gauge or a Bellows type gauge. So, how it is done I will show in the next slides. So, displacement measurement is made using a linear variable differential transformer or LVDT, and what we are going to do is to look at the basic theory of LVDT along with some circuitry details in the present lecture. So, let us look at the possible ways of doing it. Before that, let us just recapitulate the LVDT construction. It consists of a primary coil. You see here a primary coil. This is actually a cylindrical thing. I have taken the cross section. There is a core which is made of a ferrite material, and it is capable of movement in the longitudinal direction. It can move in and out like this. Either it can move this way or this way. So, that is what is indicated by this movement. There are two secondary coils, secondary coil 1 and secondary coil 2, which are coaxial with the primary coil. And if you remember your basic electrical engineering course, you will realize that a transformer is an AC instrument. That means, if the coil 1 carries an alternating current, then the flux lines will link from through the ferrite core to the two secondary coils. So, if the alternating current is impressed or alternating voltage is impressed on the coil 1 or the primary coil, the secondary coil 1 and secondary coil 2 both are going to respond to this and produce their own outputs. These outputs are also going to be alternating current, and what we are going to do is look at this output of these two coils. If the ferrite core is exactly centered, that means symmetrically placed with respect to the secondary coil 1 and the secondary coil 2, then the two outputs of the secondary coil 1 and 2 are exactly equal to each other. So, if you subtract one from the other, that means taking into account the proper phase relation between the two, if I subtract the two, I am going to get a null voltage. So, exactly how it is done we will see in a little while from now, maybe in the next lecture. So, secondary coil 1 and secondary coil 2 are going to produce the same voltage, and therefore, if these are subtracted, I am going to get the null, which means that in the under the null condition, the ferrite core is symmetric with respect to the two coils, secondary coil 1 and secondary coil 2. Suppose now we impress a small displacement either to the right or to the left. Let us see what happens. If it is displaced to the right in this case, secondary coil 2 will be linked more closely magnetically, because the ferrite core is a magnetic material, and this shaft which is shown here is a non-magnetic material, maybe aluminum for example. So, the coil, primary coil and the secondary coil 2 will have a more coupling as compared to the primary and secondary coil 1, and therefore, the secondary coil 2 is going to produce a larger voltage by transformer action. Secondary coil 1 is going to produce a smaller voltage, and therefore, if you take the output of 2 minus the output of 1, it will be a positive value. Okay. Suppose now it moves to the left, in which case secondary coil 1 is going to be closely linked to the magnetically linked, and therefore, this is going to produce a higher voltage, and this is going to produce a lower output, and therefore, the difference will be negative value. One of them will be negative with respect to the other one. Actually, both the outputs are AC outputs, and therefore, when I say positive or negative, I think we will have to look at it more carefully a little later on. So, let us see how I can use this LVDT for measuring pressure. That is our idea. So, I have shown here a diaphragm gauge, where a diaphragm is stretched between a support like this. It could be also a strain measurement in a mechanical experiment involving straining of a material. Here we are talking about pressure, and therefore, the gauge will be in the form of a diaphragm. Diaphragm is like what we discussed earlier. So, I will come back to the case of diaphragm a little later on. I will take a specific example. So, I am applying a pressure P 1 on one side, P 2 on one side. If P 2 is greater than P 1, as is shown here, the diaphragm is going to bend like this, and this rod is attached to the diaphragm, and therefore, the diaphragm will move towards the left. So, when the diaphragm gets strained like this, or it changes shape like this is going to move to the left, and therefore, it is going to throw out of balance the LVDT transducer, which is shown here. So, this will be more closely linked to the primary, and this will be less closely linked to the primary. Therefore, the voltage produced by this coil will be more than the voltage produced by this coil. Therefore, you have a imbalance voltage, which is what is a measure of the displacement of the diaphragm, and here you see that I am measuring the displacement at the center, that is the maximum displacement point. Of course, it could be kept anywhere else and suitable calibration can be done. In this case, I have shown it to be exactly at the center, and therefore, it is going to measure the maximum deflection of the diaphragm, which occurs at the center of the diaphragm. And we have a pressure appearing, which is higher pressure on this side, lower pressure on this side. Another way of doing it, let me just look at the Bellows type pressure gauge with a LVDT transducer. Here what I have done is I have shown the base Bellows element here. The pressure P 1 is applied to the inside of the bellows, and the pressure P 2 is applied to the outside of the bellows, and the shaft of the LVDT is connected to the bellows like this, and you can see what is going to happen. If P 1 is more than P 2, the bellows will expand in this direction, it will move in this direction, and therefore, this rod will be pushed to the right side, and therefore, LVDT will give you one type of output. If however, P 1 is less than P 2, it will move in the other direction. That means that whenever there is an imbalance in the pressure between the inside of the bellows and outside the bellows, there will be a net movement either to the plus side, this side, or to this side, and therefore, we get an output from the LVDT, which is going to be dependent on the difference P 1 minus P 2. So, let us look at the circuit schematic. We just have enough time to just look at this. We will have to resume from here a little later on in the next lecture. So, LVDT, how does it work? We can just show it schematically. We have a primary coil and this is driven by an AC voltage, which is usually several kilohertz and maybe a few volts, 2 to 3 volts peak to peak, and maybe 4 to 5 kilohertz the frequency. It is a sine wave which is going to drive the primary, and the core is shown here as moving up and down, and there are two coils which we indicated earlier. This is the secondary coil 1 and this is secondary coil 2, and the two are going to generate voltages proportional to the input voltage. Of course, this voltage depends on the turns ratio, this turns ratio of this to this, this to this and so on. So, this will produce a voltage equal to V 1, this is also AC voltage, this is also equal to V 2, this is V 2 which is equal to also an AC voltage. I have schematically shown it as the difference between two AC voltages, but how it is done is slightly different, which will become clear later on. So, let us look at the typical output, the block diagram of an LVDT signal conditioner. So, we have a sine wave reference generated, which is going to drive the primary coil of the LVDT. It may require a power amplifier to drive the current through this coil. Then the LVDT itself has got two coils, and we are going to amplify and also demodulate the signal, because we want to, from the AC signal which are going to come out from the two V 1 and V 2 are AC signals, I am going to demodulate. Later on we will see how demodulation is done. I will just give one or two simple ways of doing it. The demodulated voltages are filtered to remove AC component or the ripple, and what you get is simply a DC output. So, a block diagram of the LVDT signal conditioner is simply consists of a sine wave generator which is going to drive the primary through a power amplifier. The two secondary voltages are going to be amplified and demodulated to remove the ripples or the AC signal, AC part, and then through a filter, and then we get the DC output. This DC output is proportional to the change in the position of the core of this LVDT. So, if the core of the LVDT is connected to, for example, the diaphragm gauge or to the Bellows gauge, this gives you the moment. And if you remember, when we talked about the diaphragm gauge, we said that the diaphragm displacement at the center of the diaphragm is proportional to the pressure difference across the diaphragm. Therefore, this displacement which appears as a DC output here is actually proportional to the pressure difference across the diaphragm, and therefore, we can link the DC output of the LVDT transducer to the pressure difference across the diaphragm. So, in the next lecture, we will look at more details of the LVDT signal conditioning, and we will give one or two examples, and also I will consider a problem involving a diaphragm gauge, which I thought I would do in this lecture, but I think we will have to do it in the next lecture. Thank you.